The last part of our lecture today is about game theory for cooperative wireless networks. We played around with NetLogo and some artificial examples, but now we would like to bring it really to a wireless network. This work has been done by some colleagues and myself, and we have published it in some conference papers and also in the books. If you are more interested in that, you can find it on the web page. Now, the question is like this. What would happen if you would have one base station that can convey information to some devices, and these devices form cooperative clusters? Sounds familiar? That's exactly what the football stadium scenario is, right? The question is, why should they really cooperate, right? And the idea is to tell them something about the energy consumption. So the idea here is that we have such a tool. The granularity is very bad. In the middle we have the base station, and we have devices that are going around here, and they have different strategies. I want to talk you what they're doing, but when you see they're alone, there's a 1 here, which means they need to get the information directly from the base station, and 100% of the energy is needed to get the information from here. But if they cooperate, here 2 of them, they have a data rate based on the distance, a certain data rate, and they can lower the energy consumption for that. So we have a cellular technology and a wireless local area network for local exchange. Now, question is, what would happen with the energy if they're all non-cooperative? Very easy. They just download it from the base station, and they have to put in 100% of the energy. If they would just say, we would like to do something different, we would like to cooperate, all of us. So everybody get 1/5 of the energy, and then we will exchange it among each other, right? And then, of course, you need some energy also to exchange the information. The 20% that you download here, you have to exchange with your counterparts. So the question is, what is a good idea? So here you see 5 devices, and they are connected to each other. And this is strategy A, which is, we call it a nice strategy, right? They say, let's get everybody on board. And in order to get everybody on board, we have now 5 terminals, and we only need 20% of the energy for getting it in the cellular context, but we need energy for exchanging it. And because this one exposed terminal is not so close, we cannot do the exchange with 54 megabit per second. We have to drop down to 36 megabit per second, even in this communication, so that the exposed terminal can overhear it. So if you look into this energy from the system perspective, each of the terminals will use 68% of the energy compared if they would do it standalone, which is a good idea because everybody would believe that this is good. Better than doing it alone, I should cooperate. But is this the best? If you could do even something different. You could say, I have a different strategy. I just have a cooperation among the strongest in the group and let the exposed terminal get out. So here we have now cooperation only among 4 of them. They have to get a little bit more from the cellular one, but now they can cooperate with 54 megabit per second, which means they are saving a lot of energy here. So they are gaining while this guy has to do. So now every terminal only has 60%. Before, if you would include them, it was 68. And here the exposed terminal still is standalone, and he has to do it alone and gets 100%. If you now calculate the system gain from all 5 terminals, you're back to 68. So there's no real gain in saying this is better than the other, right, from the system perspective. But what will the individual do? We said real egoistic behavior is to cooperate. So is this really true? That's the question here on the lecture. Now, how we calculate this energy, that will be done later. There is one lecture only for that. And interesting is, what is the Nash equilibrium in this game? So what we did is we used NetLogo for that. And we had 2 different measurements. One was where all agents play according to one strategy. So for example, strategy A over the iteration, and then strategy B. And we show the energy ratio here, and smaller is, in this case, is better. So strategy A, if you only have devices playing strategy A, that's better. Now, if you play strategy B, that's not so good. So if you are nice to the others, it will pay off. You remember what the monkeys did with the payoff tolerance? That is now exactly what we can see here. A is better than B. The problem is, if we are not, if we don't have a homogeneous case, if we have half of the people playing B and half of the people playing A, it looks a little bit like this. So first, the winner was A, but now if we do it differently, you see that something happens at the beginning, but then strategy A is exposed and they exploit strategy A, and strategy B is winning over it. So now strategy B is the best. So in real life, when you have to expect that there are some people not behaving nicely, you may want to change your strategy also to strategy B, right? Remember the stability we talked about. So what's all about this egoistic behavior is to cooperate. So there's something what we can do. Now we change the setup a little bit. We have some players in the middle, and they are the nice guys, right? They are cooperating among each other, and they cannot get out, right? Here we have 4 different devices, and they cooperate in a nice way. And the more devices I will put in the box, the better it is. That is clear because then they can share the task and the data rates become higher. Now, what will happen if I move the bad guy, so strategy B, in the outer side of the box? Now suddenly the whole game is collapsing. So the values go up, which means it's not as good. So what happens is they're still cooperating in the middle, but if a guy from the outside means, hey, can you help me? They will help them because they are nice to them, right? But he will never help him. If he's this guy, if this is alone, nobody will help him. So what can these guys in the inner box do? The first thing is they say we will not cooperate with the others, right? That is one way of doing it, but they need cognition. They need to understand which strategy are they playing. And you can find this out as the agent or turtles did in the NetLogo example. So if you don't cooperate, you would fall back to the old curve. From the solid line, you went to the dashed line, but if you can train them not to cooperate with the guys outside, then you will fall back on the curve. But there's something better, and this is that. You can see it, that you can even improve the curve if you explain the inner guys. You should play wise only with the people that play wise with you. And if you're in need of help of cooperation once you're close to the border, only play according to the strategy of the others. So now you're not only cognitive about the strategy the others are going, you're also adaptive in changing your strategy. And then you see if the number of devices in the box is small, you can expect a small gain. If it's larger, then you will never cooperate because you will stay inside your own group and you don't need the others outside. So there is no gain to expect it. But if you have a small number of players, then you see you get a gain. So it's not the best to avoid cooperation with the bad guys. You only have to know how to deal with the bad guys. And even though this gain is very little here, I would like to come back and conclude the lecture with a one sentence: real egoistic behavior is to cooperate. And you have seen this now, the statement of Kurt Edwin, that this is true, even though it's small. You could prove it with this very small toy examples. And we will find more of these examples in the following lectures. Thank you very much, and see you soon with the second lecture.